Welcome to Magnetic Domains for Magnetic Materials. This is chapter 8.5. What is magnetic domain? A magnetic domain is a region within a magnetic material in which the magnetization is in a uniform direction. By uniform direction, I mean a singular direction. This means that the individual magnetic moments of the atoms are aligned with one another and they point in the same direction. Okay, we barely understand this. Before we go deeper, what is a magnet? This is a kind of magnet which has two poles, a south pole and a north pole. But in practical, we know better about the bar magnets, which has similarities like this. Before that, why we would learn about the magnetic domains? Why are there magnetic domains? Firstly, a single crystal of iron does not necessarily possess a net permanent magnetization. Does not possess necessarily. In the absence of an applied field, if a magnetized piece of iron is heated to a temperature above its Curie temperature is 770 degrees centigrade or 1418 degrees Fahrenheit for ferric specifically, and then allowed to cool in the absence of a magnetic field, it will possess no net magnetization. So what do we understand over here? Pure iron is not a magnetic material, and here I make things more clear. Suppose you have a magnet, then give me a magnet. This is your magnet. This was your magnet. And I broke it. Yes, I'm a horrible person. Now, by breaking it, I accidentally made two magnets out of one, which has a north side and the south side. But the magnetic fields and the magnetic stuffs over there will create two separate magnets. Like this part doesn't have a south pole and the south pole doesn't have a north pole, so they create for their own selves. And now we have two magnets, and also the both are in same alignment. In other language, we can say they both will do the same things as a singular magnet do. Okay, so we can see three pictures over here. Every pictures have domains called magnetic domains. What exactly happens here is for more and more derivation of breaking them into more and more parts, we get more magnetic spins. These are called magnetic spins. But we gradually have less effective magnetic field strength. What is magnetic field strength? This is magnetic field strength. So, this is called the domain wall. This wall actually absorbs energy from the magnetic field and make them less effective. This is called magnetostatic energy, magnetic field's potential energy. Okay, the external magnetic field lines are reduced and there is now less potential energy stored in the magnetic field. Exactly doing the reverse engineering, we can say there's a crystal iron with very less likely magnetic uniform spins in it. When we put that in an electric socket or magnetize it by any other method, the domain walls start to break like this picture to this picture and transfer the energy to create more and more magnetostatic energy. In the previous picture, we saw these lines, the curvature lines, are actually magnetostatic energy starting from here and here. So here are 5 lines, here are 8 lines, and here are many more. Why? Because all the domain walls are breaking and creating more and more magnetostatic energy, magnetostatic field forces, and then creating a whole ferromagnetic material which was a ferric at a once time. So a natural example for this experiment, this is a kind of lodestone which was hit by 1 million volts approximately lightning and turned into a permanent magnet. Lodestones are basically natural magnets because the lightning strikes makes all the domain fine aligned. I hope this is really clear now. So, magnetocrystalline anisotropy. huge name, big part to understand. Definition is a ferromagnetic material is said to have a magnetocrystalline anisotropy of it takes more energy to magnetize it in a certain direction than in others. The directions are usually related to the principal axis of the crystal lattice. It is a special case of magnetic anisotropy. Where we does where we do see over here is there's only 4 spins and there's a 6 spin. 6 spin by 6, I mean the 6 direction, and there's a 4 direction. So it's common sense that I would need more energy to break the domain walls from here than here. This part needs more energy to create electrostatic fields, magnetostatic fields. My pardon. So I can say easily this part would need less energy to go fully magnetized than this part. But between them, the magnetization rapidly increases and saturates with an applied field of less than 0.01 Tesla. So really not that a big issue for the final results. So the practical differences between the different domain types, numbers and materials of magnetocrystalline anisotropy are here presented. Domain walls. In magnetism, a domain wall is an interface separating magnetic domains. So interface separating magnetic domains means this is a domain, which are both different size, different orientated, and this has been interfered by this part, which is called the domain wall or a block wall. What it does over here is it is a transition between different magnetic moments and it usually undergoes an angular displacement of 90 degrees or 180 degrees. We see over here it has totally 180-degree rotation. A domain wall is a gradual reorientation of individual moments across a finite distance. The domain wall thickness depends on anisotropy of the material, but on average spans across around 100 to 150 atoms. The block energy, the block wall or the domain wall energy and thickness depends on 2 main factors. One is the exchange energy, E of x, which depends on joule per atom, and the other is magnetocrystalline energy, K, which is joule per meter cube. Suppose there is a block of wall crystal of iron having a domain walls where the thickness of the wall is a sigma or a delta, what you prefer to say, and an interatomic spacing, which is area A. So the potential energy U of wall is likely equal to pi square E of x divided by 2 A delta plus K sigma or the K delta, whatever you call, they're both the same. An exchange law and anisotropy law. So magnetic hysteresis. Magnetic hysteresis occurs when an external magnetic field is applied to a ferromagnet such as iron and the atomic dipoles align themselves with it. Even when the field is removed, part of the alignment will be regained, retained, and restored. The material has become magnetized. Once magnetized, the material will stay magnetized indefinitely, means they will turn into normal like some days later or some months later, but they will turn into normal because this is not a permanent magnet. So take a piece of metal and a good strong magnet, put him like this and do this. Yes, rub it like this and you will see the material, the ferric material or the magnetic material, non-magnetic, will turn into a magnetic field. We'll have the magnetic fields inside. It will just attract the metal beings. So a magnetic dipole preferred to stay always lined up. Outside of a domain, there are other domain magnets line up in the direction with the direction of external magnetic field. So this is the electron spin of ferric, suppose. So if it were a magnetic field, it will get everything aligned on a single domain. We could say a uniform direction. If we put a magnet over here, the orientation of magnet will affect the orientation inside the metal ion, and the energy goes up to the domain is opposite to external field. The energy inside, the more and more blocks inside here, the lesser energy outside. The energy goes down if the domain parallel to external. The domains are parallel, then the energy is less. So this is a type of thing we learned back in our school or college days. The magnetic force, 90-degree aligned with the magnetic change, the moving charge, and the magnetic field line, which is not illustrated by me. This is a graph I'm going to describe about magnetic hysteresis. Please pay attention. This is a metal bar or a ferromagnetic material. This is a wire connected to the battery or the power source. When I put the source on, this will charge the wire and make this bar a magnetic field will create here, and this will be magnetized. So this is the result of going magnetized and without looking for iron. When we connect the batteries, the graph will reach here, the saturate point, when your metal bar is totally 100% magnetized. So you're willing to make this a magnet, you win. Yes, it's a win-win. When you put the magnet over there and when you disconnect the battery, what will happen then? The magnetization will get over and over and over, and then gradually this will turn into normal thing, and your point will reach over here and the battery turns off. And when you again put the battery inside here, when you put the battery inside upside down, or you can say the opposite direction, this will reach over here at this point. When you put the battery at opposite polarity, and then the point will reach way down here at the totally opposite side of the first place, and the saturation point you get when you connect the battery in the opposite direction, like you have the north pole over here and the south pole over here, then you will get the opposite results, south pole over here and the north pole over there. So no, you cannot change the orientation, but yes, this is a non-magnetic material. We're turning this into a magnet. So the saturation point will reach again, and again when you remove the battery, this graph will move up to here, but you cannot truly demagnetize the effect on magnetic material. So it will reach here, but not here at the zero. No, you cannot turn this thing totally demagnetize it. You cannot turn off the magnetism at 100%. So again, you put the battery in the right direction, it will go up in the same position, the saturation. Well, you get 100% of battery or a 10% of battery. Sorry, 100% of a magnet or 10% of a magnet. It is obvious. You cannot change the magnetization. You cannot change him into a normal piece of metal again, ever again. You cannot remove the magnetic effects. So these gaps are the value, main parts of hysteresis, the lagging behind, getting back in the original substance we used, like it was a pure metal, but it's now polluted with the magnetic fields. So in short, we can convince that the hysteresis, like you are trying to take over England like a material, but you cannot just attack a country by making your own force current. Instead, you can convince the people, by people, I mean the domain, you can have England material by yourself. Is it hard to understand? So, if you can manipulate the domains of any material, you can take over the material also. So I manipulate the domains of ferric and it turned to a magnetic material. This slide has been made by me. Thank you for sticking with the boring slides.